Good morning, students. So again, coming to model fifth, that is the second topic. That is today I am going to tell you about. I will explain or I will derive the one equation, that is a forced damped vibration, that is harmonic, which is single degree of freedom system. Okay. So here I am going to use the I am going to refer the book what TV Goda first edition book. Okay, so that from that book only I am taken some images to explain you. Okay, so here this question is also very important. So here in examination they may ask you what is the inertia effect which is present in the forced vibration anta. Okay, otherwise they may ask you explain the steady state equation of a forced damped vibration, that is a harmonic force which is subject to a single degree of freedom system. Okay, so now I am going to consider one a spring mass damper system. Okay, so here the headline is forced harmonic vibration with the damping. Okay, so damping means we are going to consider here the damping system. Okay, so here I consider a spring mass. This is what I consider. This is a spring mass damper system. Okay, so consider a spring mass damper system. This is a mass, this is a damping, and this is a spring which is connected to the one end is fixed. Okay, so this is what the static equilibrium position, that is a horizontal line. So if you apply some external force, that is as the name indicate what the harmonic nothing but what the external applied force, which is in terms of what sin omega t. Okay, so here I'm going to apply some external force on the particular mass, so it will displace some position. Okay, even if you apply means a vibration takes place here. Okay, vibration nothing but what the moment. Okay, so there is a, so it will displace from one position to another position. That distance I'm drawn in the figure B. Okay, that is called as the figure B. Okay, so upon which this upon the mass there are three forces which will be acting. Okay, so here the figure B shows what the free body diagram of this forced harmonic vibration system, that is spring mass damper system. Okay, so here the because of damper one force is acting here, that is a damping. Because of spring it is going to act spring force. Because of mass the inertia force will be there, and one more is a external force, that is a harmonic force. Okay, this force going to apply on this mass system. Okay, so this is about the free body diagram, and this x is what the displaced position. Okay, if you apply force here, this mass will comes here. Okay, so here, so from this mass to this mass, that distance, that the displaced position I am going to consider is a x. Okay, so here the kx stands for the spring force, that is a restoring force, and cx is the damping force, mx is the inertia force, mx double dot is the inertia force, and f of t is a external force, that is a harmonic force, which is equal to f naught sin omega t. So this force. Okay, now according to the Newton law, okay, that is second law, inertia forces is equal to external forces. Okay, so here I've taken here mx double dot plus cx dot plus kx, so this is an external force minus f of t, otherwise you write r and rhs, so f of t. Okay, so mx double dot plus cx dot plus kx is equal to, so this goes to this direction. Okay, but we know that f naught f t is equal to what, harmonic force, that which is equal to f naught sin omega t. Okay, I give equation number 1. Okay, but we know that the normal general solution we are going to consider as what the total solution is equal to x is equal to total solution, general solution is equal to x of c plus x of v, that is a complementary function and particulars function. Okay, so complementary function we are going to consider without vibration, that is a free vibration. Complementary function we are going to consider with a forced vibration. Okay, so we are going to apply the force on a particular mass parameter in terms of mass, damper, and the stiffness. Okay, so this is you find the x of c equation, x of v substitute, that is the general solution for this undamped mass system equation. Okay, by considering the no friction forces. Okay, the equation of the motion which is given by the, there is no friction, there is no external force, means which is equal to 0. Okay, so here mx double dot plus cx dot plus kx which is equal to 0. So here we are going to consider the 0 force. Okay, assume the solution of this equation of the form with respect to the exertion force. Okay, so if you are assuming exertion force, means that is a particular solution. Okay, x of p is equal to capital X sin of omega t minus v. So x is what the displacement here, maximum displacement, where x is equal to what, the maximum displacement, that is maximum amplitude of the oscillation which is takes place, and phi is the phase angle, that is the phase displacement which is there in the mass. Okay, so differentiate with respect to x, again x of p is equal to, you are going to, if you differentiate this, means you are going to this equation. Okay, omega of x cos omega t, sin differentiation of what, cos x of cos omega t. Okay, so which is equal to what, omega x of sin omega t minus phi. So there will be a small amount of phase angle will be there, that is we are going to consider as 90 degree plus 90 degree. Okay, so this equation you give as equation number 2. Okay, so now again differentiate again we have to differentiate again x of double dot p, that is the particular function, is equal to, again differentiate with respect to x this equation. Okay, So you are going to get this, so minus of omega square x of sin omega t minus phi, so which is equal to what, omega square x of sin omega t minus phi. Here there is a 90, here 180 degree will be there. Okay, so this is a phase angle. Okay, so substitute all these values, that is x of p, x dot p and x double dot p in the equation number 2. So you are going to get this equation. Okay, substitute all the values in the equation number 2, so you are going to get this equation, that is m omega square x sin of omega t minus phi plus phi plus c omega x capital X omega t minus phi plus pi by 2. Okay, so plus k of x sin omega t minus phi, which is equal to external force. Okay, that is f naught sin omega t, so which is give equation number 3. Okay, after substituting equation you are going to get the 3 equations. Okay, the vector representation of the equation. Okay, this is the reference plane. Okay, so here initially we are going to take the omega t, so from the external force, that is this is force is the external force f naught. Okay, so from this to horizontal omega t, and phi is an phase angle. Okay, here the x is the displacement, normal displacement. From this point to this point we are going to consider the phi, and this remaining angle is omega t minus phi, so this is the difference. Okay, so here this is the force acting on that particular component. Okay, so again same formula, if you consider this triangle. Okay, same this triangle here I taken triangle, so this is what the kx minus m omega square x. So if you consider this triangle OAB, so OAB, so this is an external force, this is a damping force, this is a spring force. Okay, so with respect to phi angle, so this is a phi angle, so you are going to consider this triangle. Okay, so in examination, that is what, while solving the problem they make you these values, phi values and omega t values. Okay, if you take this those, you can solve the problem. Okay, so this is about the vector diagram. Okay, so from the figure let us consider the OAB. So f naught is equal to what, according to Pythagoras theorem, kx minus m omega square whole square plus c omega x whole square. Okay, Pythagoras theorem is square root of a square plus b square. Okay, so maximum displacement or the maximum amplitude of the vibration is going to taken as this equation. So already we derived this equation, x of maximum amplitude is equal to what, f naught by whole square root of k minus m omega square whole square plus c omega whole square. Okay, but we know that again we have to simplify this equation. Okay, if you divide by k, so f naught by k square root of 1 minus m omega square by k whole square plus c omega by k whole square. Okay, so just to simplify this equation, we know that this is very very important. This equation I am going to use in almost all the derivations. Okay, where I am going to write directly. Okay, so those times don't ask why sir you are written directly. Okay, so you have to simplify this. Okay, c omega by k, which is equal to c by cc. Okay, cc that is here the natural frequency. Okay, cc by 2m, so which is equal to m by k, which is equal to, that is what, which into omega. Okay, so this is equal to like this, we can write like this also. Okay, otherwise c by cc is nothing but what, a zeta, and cc by 2 omega we can write as what, omega n. This is a 2 by omega n whole square into omega, so like this we can also write again, which is equal to what, so 2 zeta, so this can be written as this omega n going to cancel, 2 zeta omega by omega n. Okay, wherever c omega by k is there, I am going to write this direct formula, this is 2 zeta omega n. Okay, so this is very very important for the solving the problem also. This we have to remember the equations. Okay, so if you know this, you can write here directly. Okay, c omega by k is equal to what, I wrote directly here. Okay, so x of maximum is equal to f naught by k divided by k, so whole divided by square root of 1 minus m omega square divided by k whole square plus c omega by k whole square. Okay, wherever c omega by k is there, I am going to write this. Okay, f naught by k is equal to whole divided by square root of 1 minus omega by omega n whole square to the whole square plus 2 zeta omega by omega n whole square. Okay, so this is about the maximum displacement you are going to take place. Okay, you are going to take on this. So there is a maximum constant, that is what the steady state of constant amplitude which will be there in the component. Okay, so let us assume now x of, that is a static deflection. X is nothing but what, the static deflection is equal to what, the f naught by k, where x is equal to zero frequency deflection under the action of the force f naught. Okay, so sometimes it is also called as a static deflection because of f naught is a constant static force. Okay, so again you take the ratio of those. Okay, x of maximum is equal to divided by x of s, so 1 by divided by square root of 1 minus omega n whole square to the whole square plus 2 zeta omega by omega n whole square. Okay, so here x is equal to maximum amplitude is equal to x of x is equal to, that is x of static deflection is equal to whole divided by square root of 1 minus omega by omega n whole square to the whole square plus 2 zeta omega by omega n whole square. Okay, therefore the tan phi is equal to what, the phase angle we need. So according to there, again here you can take that triangle diagram, so apply the tan definition. So you are going to get c omega by x whole divided by kx minus m omega square x, so which is equal to what, c omega, again you have to re-simplify this, you are going to get k minus m omega square. Okay, so again this equation you have to remember, this is very important, and this equation also you have to remember. Okay, these two equations I am going to use while solving the problem. Okay, so finally you are going to get the phase angle. So phase angle is equal to what? Tan phi is equal to tan inverse of 2 zeta omega by omega n whole divided by square root of that is whole divided by 1 minus omega by n omega n whole square. Okay, so just you have to remember this. Okay, this is the simplification I wrote because of this. Okay, phi is equal to again from this tan phi is equal to c omega k minus m omega square. Okay, taken as it is, again divided by k. So if you are simplify this, you are going to get this equation. Okay, c omega by k is equal to what? 2 zeta omega by omega, and that I taken this directly equations. Okay, so this is about the phase angle. Okay, so now hence the particular solution you are going to get what? Xp is equal to x static deflection sin of omega t minus phi whole divided by that square root of 1 minus omega by omega n whole square to the whole square plus 2 zeta omega by omega n whole square. Okay, so the value of the complementary function, we know this already, we derived this, can be taken as x of c is equal to, the c stands for complementary function, capital X is equal to e minus zeta omega n t sin of square root of 1 minus zeta square into omega n t minus phi. Phi is the phase angle of first angle. Okay, so if you substitute all these two values in the general solution, that is the complete solution what we are going to take on as x is equal to xc plus xp. Okay, substituted in the two complementary function and the particular function, you are going to get the final equation. Okay, so this equation is required while solving the problem. Okay, along with that two equation, this equation also is required. Okay, so the complete general solution is equal to what? X is equal to x into e minus zeta omega n t into sin of square root of 1 minus zeta square into omega n t plus phi 1. Okay, so phi 1 is the phase angle. Okay, so omega n is the natural frequency time. Okay, so plus of x of c, yes, it is static deflection sin of omega t minus phi whole divided by square root of 1 minus omega by omega n whole square to the whole square plus 2 zeta omega by omega n whole square. Okay, so this is the general solution for the undamped spring mass damper system. Okay, so this is very important, just to remember that in particular function you are going to take on the values with applying the force xc, that is the complementary function without force. Okay, that we have to take on the values and just to substitute here, you are going to get the complete solution. Okay, so this is very important, and it is sometimes they may ask you what is the inertia effect anta. Okay, that also you can write this derivation only. Okay, so here you have to remember all the symbol. Okay, so the x is equal to the x of static deflection is equal to what? F naught by k. So this is called as zero deflection. Okay, so you have to remember the symbol which you are going to use the while solving the derivation. That is what c means what, k means what, m means what. Okay, f naught means what is harmonic force and what is excitation force, that you have to remember, means you are going to get the you are going to understand clearly. Okay, so I hope you understand this definition. Okay, this derivation and definitions. Okay, so thank you very much.